of this whole chapter is to prove the existence of weak KM solution. So weak KM solution, and then surely you're gonna see that the dynamics come later. Actually, we see some flurries, I mean, here and there so far. So we can solution, I have S minus, this is of negative type. And then S plus, this is a positive type. And as I said, that we're gonna focus mainly on negative type because, they are essentially analogous to each other. So, we already defined that U is in S minus if I have that U is dominated by L plus C for some C. This is the first requirement. And by now we know that the first requirement is equivalent to the fact that U is Lipschitz. And h of x dux is less than or equal to C almost everywhere. So that's the first requirement. The second requirement is that and for every point, any point x in the torus, we can find a calibrated curve gamma, of mapping from, an infinite interval from minus infinity 0 to the torus with gamma 0 equals to x. So, as mentioned, we have been able to completely understand the first claim, and its equivalent claim. So that's good. So now today we're going to try to go further to understand a bit better about the second claim, what it means, and certain deductions from that sort of requirement. Okay. So again, I mean, the point now is sort of like to understand what does it mean by given any point we can find a calibrated curve ending at that point. So you're given any point x in the torus, you can find a calibrated curve gamma mapping from minus infinity 0 to Tn with gamma 0 equals to x. Okay, so that's sort of the roadmap of what we are doing. And one of the important results that we're gonna do today, today we're gonna do two things, but the first important point is that first important point is gonna be that U is in S minus. If U in S minus, then I must have that C equals to C naught. Okay, so that's going to be a very important claim that we're going to prove today. Meaning that, C can't just be arbitrary. It has to be exactly C naught in order for us to have a calibrated curve mapping from an infinite interval to the torus. That's exactly really important. Okay. And then I'll mention the second important point later as time goes. Let me just highlight it. Okay, so before doing so, then I recall the definition. One of the definition of C naught here is the infimum or possible C, right? You try to push further and further for the C. You take all admissible C, so that there's a U Lipschitz satisfying the inequality, and you take infimum of all of those. And last time we actually proved that C naught itself is also admissible, right? So we proved that actually there exists a function U, that U is also less than or equal to L dominated by L plus C naught. In other words, C naught is also admissible. So I write U naught to be U, just to say that it's sort of like a clearer dependence on C naught. Okay, and also that so remember also here that that we have two other formulas. The first formula was that you write it for the Lipschitz functions, then it's the infimum of all Lipschitz functions and essential supremum h of x d phi x. And then there's also the other formula, which is clearer because we are only requiring functions to be C1 or C infinity. Okay, so those are the two others that we have, and they're important. And as I said, they are only being written down about 20 years ago by both dynamical people and PD people. Um, and you have seen the proof, right? There are dynamical proofs. The proof I presented, the regularization is simpler by using PDE. It's we are now free to go between the two lands whenever there's a easier way to say things. Okay. So now this is exactly the results that's gonna imply the first thing I mentioned, the first important point. And the result is rather simple, right? We say that, if I have gamma is a calibrated curve, ULC calibrated curve, and if gamma maps from an interval of infinite length, then I must have that the constant C is C naught. Okay, so that's remarkable, right? We don't need actually for many curves. We just need that if there is one curve that is calibrated and mapping from an infinite length interval, then it must be the case that C is the critical value, C naught, an additive eigenvalue, whatever. And this is what Sun asked earlier. If you have it's a calibrated curve, and together with the fact that it's dominated by L plus C, then it's becoming a minimizer on extremal curve. Okay, so that's require both. Hold on, actually, did I give me 1 second? Did I forget one assumption here? Yes, I no, this is exactly the case. I think I assume this implicitly, but I should have said that U is dominated by L plus C. Otherwise, otherwise I don't have that property. Okay, sorry about that. So U is dominated by L plus C, and then if gamma is such a calibrated curve, mapping from an infinite length interval, then C has to be C naught. Okay, so let's prove it. Okay, so let me sum it up here. So U is dominated by L plus C, and I is an interval of infinite length, and I have gamma mapping from I to the torus is a calibrated, hence, because again, it's dominated by L plus C, right? Hence, a minimizer. Writing is not good. If I have these 2 points, then I would imply that C equals to C naught, which is the minimum value of all possible C. Okay, so that's I think again that's a really beautiful result. Again, you see that we are sort of getting more and more to calibrated curves of sort of infinite length intervals because we want to study their dynamics later on. Okay, and you see here comes the proof. The proof is actually simple. Okay, so let me summarize it. I have U is dominated by L plus C for some C greater equals to C naught, right? Or equivalently, you have H of X dux is less than equal to C almost everywhere. Earlier in the early result I recall today, we have that U naught is dominated by L plus C naught. And again, this is from the earlier theorem that we proved, right? C naught is admissible, meaning that we can find such an U naught. We did it last time by approximations and passing to the limit by Azela-Ascoli theorem. Okay, so those are the 2 points that we have. We have U dominated by L plus C and U naught dominated by L plus C naught. And so we're gonna just recall exactly the two and we compare the result, right? The key point that allows us to compare the result is the fact that on one hand, I'm highlighting things on the left panel now. On the one hand, you know, because gamma is calibrated or minimizer, it satisfies this equality for any AB, right? On the other hand, gamma is an arbitrary curve for other functions, right? So, you know, the first thing I'm using is that this is a minimizer, okay, or actually just definition of calibrated curve. The second thing I'm using is just that gamma is an arbitrary curve, right? It's an arbitrary curve, and because U naught is dominated by L plus C naught, so I have inequalities, right? So in the second point, I have that the action functional is always greater, acting on L plus C naught is always greater than equals to U naught gamma B minus U naught gamma I. So this allows us to compare, you know, the two sort of like two lines of computations, right? You know, and when I am able to compare the two lines of computations, the key thing here is that I'm able to sort of the Lagrangian goes away. I'm able to compare the C with C naught, right? So that's why that when I subtracting the two, I have C minus C naught times B minus I is less than equals to the difference of U minus the difference of U naught. This is not an issue, okay? And this is another point that I'm using compactness, okay? So what I'm highlighting is that the non-compact setting could be hard. It's really important, but it could be hard. If you're dealing with a non-compact manifold, then you got to be careful, okay? So here I'm dealing with the fact that we are in Tn, which is compact. And actually its diameter is root of n, right? I mean, we talk about this. You take this is the torus. You know, again, you think of it as 0, 1 to the n, and the diameter is sort of exactly going from here to here. Well, I mean, again, okay, diameter of the unit cell is root of n. You know, because I'm taking the distance from the point itself, so it's nonsense. But let's say that I'm taking the diameter of the unit cell is root n. So clearly that you have U and U naught are Lipschitz. You have U of gamma B minus U of gamma I going to be less than equals to the Lipschitz constant times gamma B minus gamma I. And because you are in a compact manifold, this is bounded by root of n in this case, or in general, if you have a compact manifold with the boundaries, just bounded. Okay, so this is bounded. Same for the difference in terms of U naught. So when you combine the two together, you have that the right hand side is bounded. That's what I'm highlighting here, you know. And clearly that the left hand side is the difference of C minus C naught minus B minus I. And clearly because of the fact that I can let the interval, the length of interval going to infinity, that must let me conclude that C is C naught. So that's really, really beautiful. This is really a dynamical proof. Um, uh, that's really an equivalent PD proof, but it goes in a different way. It's very different. We gonna talk a little bit about that if I have time eventually. Okay. So this is exactly the corollary. I mean, the important corollary. I'm putting a red box around it now. And that tells us that, you know, again, to consider weak KM solution, we only need to focus on the smallest possible critical energy level of H, which is C naught, right? Oops. And let me say it right away that sometimes I'm going to write C naught to be C subscript 0 because sometimes I might just forget. Yeah, so that's the first very important point. You know, again, it looks very simple because we have developed step by step until this point that the result just sort of like suddenly becomes rather, you know, like elementary. But I wouldn't say so, right? I mean, if we have like this claim from the beginning, like if I only introduce to you the definition of Wickham solution and tells you that, okay, C has to be C naught, then it would be quite unclear. But I mean, after developing everything steps by steps, and I hope that is clear. Any question for me up to this point before I move to the second important point? Any question, concerns, or discussion? Let me pause a little bit in case you have question. You know, again, just pick up place or type in the chat if you have something to talk about. Okay. Yeah. So seemingly it's okay. It's clear enough up to this point. So the okay. Thank you. Yeah. Again, I mean, so let me also reiterate that the goal for our class is to give you some certain viewpoints, and you could see that the viewpoints between dynamical system, Hamiltonian dynamics, and analysis PD are rather close. And I'm hopeful that you can see certain big pictures and maybe utilize certain ideas for your research or for your, you know, maybe intuitions or purposes later. Who knows, right? You know, I also myself have been in, for example, a lot of topic classes, topic courses that I'm just enjoying. I haven't used them at all, but you know, whatever. Anyway, so you know, that's the, you know, whatever. Okay, so so now the second point is it's you know, is how should I say the second point? The second point is actually very important. Uh, it's not very actually very clear from what we are talking about, but you know, once you see that, then you're gonna see that it's really remarkable in the viewpoint of analysis. Okay, I mean, not to mention PDE, but before that, let me just give you the this note, because so far we have only talked about, again, I recall the definition about S minus from the beginning already, so I don't have to repeat it here. But notice that so far we haven't proved the existence of negative and positive Wickham solution. We have only been talking about it. We have been analyzing the first part, right? And now we are moving to the second part. Eventually, in this chapter, I guess that in next couple of lectures, I don't know what our speed, so I have to be careful. But we're going to prove the existence of Wickham solution. So that's going to be the goal of this chapter. But for now, let's analyzing such solution first. And what is really remarkable is this theorem. I'm gonna actually give you a just a picture, sort of like description of this theorem, and it's a very important theorem. I thought about it, and I think that we cannot finish it today. So I'm gonna put just prove the first part, that is easier, and leave the second part. It's not too hard, but it takes some care to prove it. Okay. So what I'm going to do is the following general theorem about the relations between U and calibrated curve. So that's the second important point, right? So I should say that this is sort of the relation between U, which is bounded, dominated from above by L plus C. And again, this is equivalent to the fact that U is Lipschitz, and h of x dux is less than or equal to C almost everywhere. By the way, the content of a Lipschitz functions and understanding at what points the function is differentiable, at what point the function is not differentiable, it's a very hard topic that is still being studied extensively in analysis, classical analysis up to this day, because there can be very weird Lipschitz functions with very weird set of singularities. So if I'm only writing that U is a Lipschitz function and it's only differentiable almost everywhere, then most of the times I cannot describe very nicely the the sets of differentiability of U. Okay, so we're gonna discuss the relation between this one and gamma mapping from AB to Tn, which is a calibrated curve. And again, because it's dominated from above by L plus C, so hence minimizer. Okay. So those are the two objects that we're going to try to discuss more, the relation. And it turns out, okay, let me try to draw a picture. So again, it's a naive picture anyway. This is gamma A, this is gamma B. And because it's calibrated, we have shown that in any subinterval it's still calibrated, or it's still a minimizer. So the first claim is regular. That's what I'm going to prove first. I'm going to skip the first claim and describe to you right away the second claim, and I mean how important it is. So that's the second claim. Now it's going to tell me that then U is differentiable at gamma t for all t between a and b. Okay, so that is a remarkable result, right? Because as I said, if you have a Lipschitz function, you have absolutely no idea. I mean, we know that it's differentiable almost everywhere, but it can be, not differentiable at a set of measure 0, and that set of measure 0 can be very complicated. However, this theorem says a very remarkable thing is that if I have also a given calibrated curve with two endpoints, gamma A and gamma B, then our function is differentiable at every single point in the between, okay? You take any point gamma t here, then you have that u is differentiable here. Okay, so for any given point, what I need is sort of like to be able to find a tiny interval around it so that I can go to the left and to the right. And I know that then I know that my function is differentiable there, and it's clear that it might fail at the two endpoints. So I think I put a remark here. Maybe not. Okay. So also a remark here is that maybe I put it down, whatever. Okay. However, you might not be differentiable at the two endpoints, gamma I, gamma B. Okay. Yeah, so I would say that again, from analysis and PD viewpoint, this is a remarkable result because it tells us exactly your function is differentiable, and it's only might fail at the two endpoints of your calibrated curve. Okay, and okay, so why is it really remarkable? Well, now let's talk about Wickham solution, assuming that we have a Wickham solution. Okay, so assume for now that we have u in S minus. Okay, that is surely u is dominated from above by L plus C naught, or equivalently u is Lipschitz. H of x du is less than or equal to C naught almost everywhere. Okay, and again, the first point is fine. Is I have been repeating it forever, I guess. Second point is that for any x, we have a calibrated curve, gamma mapping from minus infinity to 0 to Tn with the endpoint gamma 0 equals to x. Okay, let me draw again the gamma. It doesn't have one endpoints, right? So it only ends at gamma 0 equals to x, but earlier it's anything. We have proved that this is a minimizer, and then we have proved that this is CK, right? Satisfy Euler-Lagrange equation, so on and so forth. Now, the second claim is that at any point in this ray, because of the earlier point that I just said, right? If it's any point in the between, then it's differentiable. So clearly what is really remarkable here, and this is why NPD is called backward characteristic, is that you from a point you can find a whole ray going from minus infinity to that point, and your function u is differentiable in this whole ray except maybe only the endpoint. Okay, this is why it's amazing. Okay, then actually u is differentiable at gamma t for all t from minus infinity to 0, excluding 0, and you might fail to be differentiable at gamma 0 equals to x. So it might fail to be differential at the endpoint. And now again, in dynamics, sometimes that, especially in 2D, when you have a sort of a simple topology, just a plane, and sometimes you have a bunch of those calibrated curves, and they can foliate, or they can fill in the whole torus or something like that. Then clearly this is going to give us a very good description of what, sort of like still abstract sense, that you have your function is so nice, it's just differential in the whole ray going backward. Okay, and then it seems already there's a set of points that your function is not differential, it's kind of tiny, right? But okay, still there can be a lot of endpoints, but at least this is a very, very interesting thing. Okay, so we're going to prove this second really important point here. That is differential at this point in the between. We're going to prove it next time. Yeah, I wouldn't say that it's too hard. I would just say that it takes some time to sort of like zigzag around a little bit and sort of use the ideas just to move back and forth. We have seen that idea in our class actually. Okay, again, tell me if you have questions or concerns. But now I'm going to prove the first claim. Let me highlight it now. The first claim is that if we know your function is differential at gamma t, again, first claim is for any t in the between a and b, including a and b, because it's about the claim that if we know that it's differentiable, okay, then, this is of expectation that du is equals to dvl, right? That's, that's quite of expectation. And we also know that the Hamiltonian acting on gamma t, du of gamma t is at the energy level C, right? Okay, so the second claim is the most important claim in this point is going to be done next time, I guess. Okay, so let's do the proof. Actually, we have done this, we have done this because the first point, okay, let me just say the first this is not too hard, too hard, as we assume that the u of gamma t exists already. Okay, what is hard is really to prove whether it exists or not, but when it exists already, then that's not an issue. Okay, again, I mean, you can assume that t is less than b, because if t equals to b, then you can approach it from just one side, approach it from something less than b approaching b, because you see that in this proof I'm only using one-sided approximation, and that's fine. Okay, so I'm assuming here that this is a, this is b. I'm assuming that t is less than b. Okay, so without loss of generality, we assume that t is less than b, and we're gonna take t prime here greater than t and approaching t. Okay, then we're gonna take t prime in the interval t to b, and we're gonna let t prime converging to t. Okay, and you can see, I mean, I'm not doing anything crazy, right? I'm just sort of like using exactly the fact that because it's a calibrated curve on a big interval, then it's a calibrated curve on any sub-interval. In particular, I'm using the fact that it's a calibrated curve on the interval from t to t prime, right? And that means that I can compare the values. of u of gamma t prime minus u of gamma t equals to the action functional from t to t prime of L plus C, right? And then, you know, as we said, we're gonna let t goes to t prime goes to t from the right, yes. And, you know, we're just gonna take, you know, u of gamma t prime minus u of gamma t over t prime minus t, and we know that as t prime goes to t, you know, t is fixed, right? U is differentiable already at that point, so we can just use chain rule, right? To see that this equals to du of gamma t dot with gamma prime of t, gamma dot of t. Again, also remember that I'm using implicitly here that gamma is ck already. That's, you know, the content. So this is quite interesting, right? The content of the first 10 lectures was about minimizers, regularity of the minimizers. And now we are in the, like, the next 10 lectures, and we are in the sort of discussions about WCAM solutions, and we are using already implicitly a lot of things we developed in the first 10, right? This is the second 10, and it just naturally sort of hidden there all the times. Okay, so I'm good because u is differentiable here, and then gamma is ck. Okay, so I'm using exactly that. This fraction is gonna go to what I'm just writing down here or here, right? And then the right hand side, you know, we are just dividing by t prime minus t, and we're gonna use, you know, the mean value theorem, or, you know, you can just use epsilon delta, whatever you want. By the mean value theorem, as t prime goes to t, it just converges to L, acting on gamma t gamma dot t plus the normalized constant c. Okay, and you subtract it, put it to the left, you would end up with du gamma t dot with gamma dot of t minus L equals C, right? And again, I'm just using the fact that h of xp plus L of xv, again, is greater than or equals to p dot v, right? Because it's just the duality inequality. So, you know, the here that you have, you know, du dot with gamma dot minus L of gamma gamma dot is just going to be less than or equals to h of gamma t du of gamma t, right? So that allows us to conclude in this red box. I'm sort of putting around it here that h of gamma du gamma is greater than or equals to c. On the other hand, du is differential at gamma t, right? So by the previous result that we proved, also that I'm using it hiddenly here, and also thanks to your questions earlier, that at any point of differentiability, I have this inequality, okay? So du is differentiable at gamma t, u is differentiable at gamma t, so I have the converse inequality. Combining the two things together, we must have the equality, right? So we must have that h of, h of gamma t du gamma t equals c, right? And then we also must have that, what I'm highlighting here, because this is where equality must happen, right? When it must happen, then P is du of gamma t must equals to dv of L of xv, right? Xv is gamma gamma dot. Okay, and that's that. Yeah, so I'm quite sort of like good on time today. You know, I stop a bit exactly on time so that we have time for discussions. So again, let me just recall the 2 points for today, and then we can discuss. So the first important point was that we see that in order to consider Wickham solution, we only need to focus on C naught, which is the lowest possible energy level in which we have existence of U, right? In this case, it's U naught. And the other thing is that we start to see that there's a clear relation between, where is it? Give me 1 second. The second point, oh here. So the second point is that we start seeing the relations between U being dominated by L plus C with calibrated curves. It turns out that the calibrated curves gives us points that the function U is differentiable there except the endpoints. And especially in the case that if you have a whole ray going from -infinity to 0, then you have that your function is differentiable everywhere except the endpoint of the ray. And again, I mean, this is remarkable because this is telling you that PDE gives you the equations, the hidden structure gives you something more than just crude um, property of a Lipschitz function. So we are using something much deeper than just a Lipschitz function, right? So that's sort of something important. And you please keep in your mind that in order for the functions to be differentiable at the point on your calibrated curve, it normally has to be in the between, meaning that I can sort of go a little bit to the left and a little bit to the right. And I am hopeful that I can demonstrate that fully to you next time. At the end point, here, gamma 0 equals to x, it's not differentiable if I cannot move further to the right, okay? Yeah, maybe this is an important remark. This is just purely speculation at this moment, so remark. Take U to be a Wickham solution of negative type and fix an X in the torus and let gamma mapping from -infinity 0 to Tn be a calibrated curve such that gamma 0 equals to X. Again, I'm keep repeating myself many times. This is gamma 0 equals to X. Geometrically, if we cannot push our calibrated curve further past X, then U is not differentiable at X. Again, this is purely speculation. So what be the scenario that I know that our function is differentiable at that point then? Well, again, purely speculation. If you can push your curve, your calibrated curve a little bit further to the right, you can sort of connect it a little bit more to the right. So instead of having your calibrated curve defining from just -infinity to 0, if you can define from -infinity to some delta Tn for some delta greater than 0, meaning that you can continue it a little bit to the right, then use differentiable at X there. Okay, so that's sort of a very speculative picture, but it's really beautiful. Okay, yeah, so we have time for questions. Sorry, I was just saying 1 minute and I went on for 5 minutes. Any discussions or anything that you want to talk about?
Yeah, is it typical that you don't have maximizers for all time?
Yes. Right. So there are gonna be some other objects that you have your whole sort of like that's going to be something called the Aubrey set, or the curves that you can have the what's the name of it, two-sided minimizers. So two-sided minimizers meaning that you're going to have a minimizers going from R to the torus. So it can go for all time, and in that case, and your function is differential in that whole line and not whole curve. So that's called two-sided minimizer. Uh, it's more typical that you're gonna only have rays that are um, that are um, that are of this nature. And in fact, this is a notion that is related to PDEs. That if you have seen like shocks in PDEs, that coming from Burger's equations or first order equations or some other kinds of PDEs. For example, there can be shock waves that the wave starts smoothly, but you see the picture, right? The drawing, that it can sort of have fingers and stuff like that, and it can break down. So when you draw the characteristics, then characteristics at first they're nice, they haven't run into each other, but when they meet each other, it's exactly this point X here that I cannot continue my curve past that point because it has shocks meeting each other there. But if I go backward, then it's fine. I'm not seeing any shocks. Anyway, yeah, but yes, that is an absolutely valid point. So there's absolutely a notion of two-sided minimizers that accounts for the fact that you can go forever. But many times that you're gonna see that we can't. We have to stop.
I see. Thank you.
Yeah. Thanks for the question.
So this thing that's up on screen right now, if
Mhm.
we can extend the curve a little bit past x, then u is differentiable.
Mhm.
Can we do a converse to that? If u is differentiable, then we can extend the curve.
Yes. Yeah, but that gonna require a bit more of you know. Yes, but uh, yeah, but for now, let's be speculative, okay? Uh, it's gonna take a little bit longer to do that, but yeah, maybe you're gonna see some of the ideas in the next lecture, and as I promised, we're gonna try to go as deep as we can here to understand the nature of the problem, but also that you can think about this in terms of characteristic method that we talked about the other day. That if you start with something, if your initial data is something nice like C2 or something, then you can run the characteristic a little bit, from minus delta to delta, and that's exactly what I meant here. But here I have to be careful because I'm only talking about that one point, right? If it's differential at one point, can I extend it a little bit? So I have to be very careful. And this is very delicate manner. um, Top expert in the field, like PD people are still working on this, and then we also have some very difficulties, very sort of substantial difficulties to understand the set of singularities of, of this thing. Um, for example, my friend Yifeng Yu and I, we have been stuck on this kind of very delicate points forever. And also recently there was a talk by Albert Fateh, the author of the book on Wickham theorem, that also talks about the set of singularities of distant function, just a distant function, okay? Uh, and this is exactly one of the point, like can um, so I mean, because he's more in topology and geometry, so the question was that, can you show that the set of singularity is topologically connected or not? Such kind of question. So it's really related to those endpoints here that you cannot go further. Yeah, and this is beautiful. Uh, yeah, I would say that sometimes it's too hard. But, you know. So maybe an honest advice here is that um, I know many top experts working on classical analysis, like Mariana Chona at Chicago and others. They have been working on just sort of characterizing singularity sets of Lipschitz functions. And those are very hard questions. I mean, I forgot what question I had, but I also had one question. I have been thinking about that for a few years and I didn't get an answer. But the key thing is that I think the question I had was not answerable because of the fact that it not just a Lipschitz function, but it satisfies also a PDE. So if it satisfies something more, then like the result that I'm presenting here, we should exploit more the nature of the problem, not just thinking of that as just a pure analysis problem. So that's my 2 cents advice, because I'm also stuck on such kind of questions. So, so when you have further information, then maybe that kind of further information also gives you some further content. And also, this is also related to some regularity question that I also have been thinking about for uh, maybe uh, 2 years now, also on just characteristics of some singular Hamilton-Jacobi equations. Like, can we prove that we can go on forever? Like, we are not crossing, and it's not easy. Yeah, but I thanks for the 2 questions that you guys asked. As always, that again, I mean, this is a topic because I know that it's harder for us to interact at this moment, but all the times, this time or last time or earlier times, that all your questions make a lot of sense. Okay. Anything else for now? Yep. So thanks a lot, you all, and we are done with our 6th week, which is remarkable. We are nearly the mark of half of the semester. I think that so far so good, and thanks a lot for your patience. And let's try to get something done. Seriously in this crisis, right? Not just sort of hanging out. Yeah. So stay safe and healthy, and have a great weekend. I'll see you on Monday. Okay. Yeah. Thank you. Bye.